Hi, I'm Krista Campbell. Welcome to the third webinar in our Arc Hydro in Action webinar series, Arc Hydro, Hydrology, and Hillslope. This webinar is being recorded. The recording will be posted on the webinar registration page and available for on-demand viewing. You will receive a follow-up email that includes links to this page, and it can take several days to publish the recording, so expect it to be available next week. The webinar includes several polling questions. Please participate in the polls. We really appreciate your responses. We have included QR codes within the presentation. You should be able to scan these codes with your mobile phone and access resources. If you're not sure how to use QR codes, don't worry. My colleague Mariah will be sharing links in the chat dialog box. I encourage you to post your questions in the questions dialog box throughout the webinar. We will answer as many questions as time allows. At the end of the webinar, a survey will launch. This is a short survey. It'll only take a few minutes. Please take time to complete the survey. We do look at it. We check out what your answers are. So we appreciate you just taking a few seconds to complete the survey. If you missed either of the first two webinars or would like to watch them again, a link for the on-demand viewing can be found on the webinar series registration page. And one last announcement before we get started, I'd like to highlight the Applied Meteorology Using GIS webinar series. This might be of interest to you since there's no hydrology without weather. Let's get started with a polling question. You know, I mentioned the first two webinars. We'd like to poll the audience and find out if you attended these. Did you attend or even watch on demand either of the first two webinars? Yes, you watched Arc Hydro in ArcGIS Pro. Yes, you watched Arc Hydro Flooding and Forecasting, or no, you missed these webinars. It is a multiple choice, but you can select more than one. So if you saw both of them, just go ahead and select both of those. Looks like about half of the audience so far has seen both of the first webinars. Great, we appreciate you guys joining our webinars. Still have some attendees voting, so we're going to leave this up for just another couple of seconds. Great, okay, it's sticking pretty close to 50% has seen both webinars. We've got about 34% saying they haven't seen them, and not everyone's voted, but we're pretty close. So I'm going to go ahead and close this poll. Thanks everyone for answering the poll. I appreciate it. We have four great presenters today. Dana is a postdoctoral scholar jointly appointed through the University of Wisconsin-Madison Aquatic Sciences Center and the Wisconsin Department of Natural Resources with a PhD from UC Berkeley in surface hydrology. Her research builds process understanding of hydrology to support water resources management. Anneliese is a PhD candidate in environmental planning at UC Berkeley. Her research focuses on developing a better understanding of hydraulic processes in urban areas and creating frameworks and tools to integrate understanding into management and planning. Gina is a technical consultant and member of Esri's Arc Hydro team. Prior to joining Esri, she completed her PhD at the University of Virginia with a focus in hydrology and informatics. And you all know Dan Jokic. He is our water resources practice manager. His education and degrees are in engineering. He has more than 25 years of experience supporting water resources at Esri. Welcome everyone. Thank you for participating in our webinar today. We are going to have Dan get started.
All right. Thanks, Krista.
No problem.
And what we'll do today is we'll first go and do a quick review of the first two webinars. Then we'll discuss some of the statistical hydrology and stream stats in particular, dive into exciting new stuff in Arc Hydro related to Hillslope hydrology and critical duration with Dana and Anneliese, and then finally do a quick look at distributed hydrologic modeling in GIS context with Gina. And we should have some time to address a few questions. So let's revisit some of the key points from the first two webinars. We'll start with what is ArcHydro. We said that the idea behind ArcHydro is to provide GIS framework for development of integrated analytical systems for water resources. It includes the data model, the tools, the workflows, and the community of users with common interests and patterns of use. The ArcHydro community page, or formerly known as GeoNet, is the gateway to all ArcHydro resources and environment to share information and experiences with other users. So it's not only for interaction with us, but among our users as well. Basic ArcHydro elements are available for free through the community page. Most tools are available both in ArcMap and ArcGIS Pro desktop environments. And the development of new tools is now primarily done in Pro with a port back to ArcMap. For fee offerings include training and consulting, and if you're interested in those services, please contact me. In ArcHydro, we have many tools and workflows in many different areas of water resources. You will most likely never use all of them, probably 30 to 40 tools that are specific to your needs. And as you dive into ArcHydro implementation, there is a lot of documentation to guide you through it. All these documents are available on the community documents page, and soon we'll be adding new docs dealing with Hillslope hydrology that we'll talk about today, and the hand workflows that we talked about last time. And did I already say that ArcHydro is free? And in our second webinar, we talked how there are different methods within GIS context to define the floodplain. And we focused on simple methods, hand method in particular, that use only topographic and optionally observed data to define flood extents. In our final webinar in April, we'll revisit this topic and focus on more complex methods based on hydraulic modeling. We also talked about flood forecasting and flood impact forecasting, and what are the key components of such a system, and so that we can identify when bad things will happen, where they will happen, and who will be affected. And we started an important discussion that will continue during this and next webinar. Basically, we said that models are not truth, they are an approximation, that we are still going to use them, and we will not wait for perfection, as that perfection will never come. And lastly, it is your responsibility to understand the tools and models you are using, and that includes the data, and to interpret the results you are getting and evaluating if they are good enough for what you are trying to accomplish. So there is no magic, just good hard work. And now to today's presentation. So today we'll dive into the hydrology portion of our GIS hydro modeling cycle. In a typical ArcHydro hydrology workflow, you will follow these steps. First, you'll do the terrain pre-processing. If there are any specific modeling requirements that need to be addressed, they should be captured early in the process and incorporated in your terrain pre-processing. Next is the watershed or sub-watershed delineation, depending on the type of the analysis you are doing. The next step would then be characterization of the drainage areas that have been determined. And finally, application of these watersheds and drainage areas and their characteristics to specific hydrologic models. As an example of statistical hydrology, we'll talk about stream flow statistics and in particular StreamStats. StreamStats is USGS program that is used to calculate peak and low flows for ungauged locations. The engine behind calculations is a regression equation that relates stream flow statistics to basin characteristics. These equations are developed by USGS and for each state in the US and are done in collaboration with other partners who usually foot the bill and fund the analysis. Similar methodology is applied in many other countries in the world under different names and by local organizations. So it's not just a US thing. The regression equations are derived using statistical methods using observations and flow frequency analysis at existing gauging stations, and relating those flows to basin characteristics. Typical equation might look like this. In this example, 100-year flow at any location is a function of the area, mean basin elevation, and some kind of shape factor. The equation coefficients are calibrated based on observed values. There are many of these equations, one for each frequency, let's say 10 of them, and each region has its own set of equations, and each state has multiple regions. In this example, we are looking at the equations that are from Idaho. So there are hundreds of these equations with thousands of coefficients. These equations and coefficients are maintained in the national database to just make sure everything is right. To use the equations, it's simple. For your point of interest, you determine its contributing area and relevant area characteristics. Plug them into appropriate equation for your region and frequency, and you get a flow estimate for that location and frequency. There are many characteristics used in regression equations. There are over 200 different ones. What is really interesting is that there are only a few of them that are actually used in several places, and only one that is used everywhere, and that is the contributing area. Very much like rational method, only on statistical steroids. So what do we do with GIS to support this? Well, almost everything. Everything we talked about so far, both terrain preprocessing and watershed delineation and characterization, are used in development of equations, as well as in the application of the equations to users' point of interest. GIS provides processing and data infrastructure that can be applied consistently and efficiently in this process. The only thing that is not done in GIS is statistical analysis, which is usually done using dedicated statistical software. StreamStats is implemented as a web application developed and maintained by USGS. It runs our hydro watershed delineation and characterization as a geoprocessing service in the background. It is implemented on a state-by-state basis, and while all states have the same base functionality, some have additional capabilities specific to that state. Also know that not all states have StreamStats implemented. While regression equations for those states do exist, their web implementation does not. Let's do a StreamStats demo. This will be an abridged, shorter version. We'll start with StreamStats website. First, you identify the area of interest and zoom in closely until detailed stream network appears. It will have a jagged look. These are synthetic streams that are derived during hydroterrain preprocessing workflow, and they're used to snap the point of interest so you ensure that you are getting a good drainage area. You click on the Delineate button and pick the point of interest. Ideally, place the point on one of the blue cells. You will get a message that the selected point is valid and that delineation process is being executed. After several seconds, the delineated watershed is presented. If delineation looks correct, you can move on to the analysis part by clicking Continue. If not, you just delineate the watershed until you get the results you're expecting. Once the computation is completed, you have the option to select the type of report to produce. In this case, I will pick the peak flow statistics and click on Continue. The final report is produced with basin characteristics and various peak flows and their statistics. This report can be printed and resulting data downloaded. StreamStats has comprehensive online help and training and several more options besides the ones presented here. It is a great starting point for watershed delineation and characterization, even if you are not interested in flow statistics analysis. An analysis like this in the past using manual methods took anywhere from few hours to several days, depending on the size of your watershed. And if you did it 3 times, you would get 3 different results. Now you can do this within few minutes with reproducible results. Stream stats or similar method, for example, debris flow calculations, can be implemented within desktop environment. You'll need the developed regression equations and data for the variables of interest. You then use GIS to delineate watershed and extract characteristics. Once you have the characteristics, you can plug them into the equations either using an external application or directly within GIS environment. Here is an example where the basin characteristics were exported into a pre-configured Excel spreadsheet with all equations already preset. This gives you capability to easily tweak watershed characteristics coming from GIS or even play with the equation parameters if necessary. For example, if you want to see the sensitivity of the results both to the changes in values of characteristics or parameters, and this way you can build a confidence in your results. And with that, let me transfer over to Dana and Anneliese, who will talk about ArcHydro Hillslope. And we'll start with a short poll. Krista?
I've got the poll coming right up. Dan, let's take a look. Have you used the rational method for peak flow prediction? Yes. Yes, but only in educational course, or no? If everyone would just take a few seconds to respond. Caught the audience selecting their best choices. Have you used the rational method for peak flow prediction? Yes. Yes, but only in an educational course, or no, you haven't used it. The votes are coming in, Dan. We've got about half the audience voting right now, with about 19% saying yes, they've used it, about 20% saying yes, but in an educational course, and 60% saying no. We still have some people voting. Boy, they're coming in quick. Thanks, everyone, for participating. We're going to give you another few seconds, get those last-minute votes. Are you surprised, Dan? About 20% is saying yes so far.
I was muted, sorry. Actually, I don't know. You know, we're all trained on that, but it will really depend on whether these are our engineering or GIS people. Okay, well, everyone, I gave you as much time as I could. We have most of the attendees voting. The final poll is 61% saying they haven't used it, 20% saying they've used it in an educational course, and 19% saying yes, they have used it. And with that, we're going to pass it over to Dana.
It is cool to hear how many of you have used the rational method versus haven't used it before. I'm going to give a little background on the rational method later, but it inspired a lot of the work that I'm going to be talking about today. Anneliese and I are going to give an overview of the new tools we've developed in collaboration with Gina and Dan for Hillslope scale runoff analysis. These tools are the culmination of my PhD work at Berkeley and Anneliese's as well, and they involve a lot of wonderful collaborators, including Mary Nichols at the USDA and our advisor, Sally Thompson. When I first met Anneliese, she suggested that we could implement this work into an ArcGIS toolbox, which seemed straightforward at the time, but it wasn't. We got in touch with ArcHydro almost 2 years ago at this point, so it's really exciting to have the tools complete and publicly available to share with you today. So I'm going to start with some background and motivation on hill slopes and curvature, and then get to how this relates to the rational method. And then I'll turn it over to Anneliese to show you the new ArcHydro functionality and give a demonstration on how to use it. Hill slopes are defined by their position on a landscape, which is upslope from streams. They don't have well-developed concentrated flow paths, but they serve a really important hydrological function of delivering water and sediment to streams. We can think of watersheds as a bunch of hill slopes connected by a stream network. And this representation can be used for numerical modeling, with the advantage that it's numerically simpler than distributed modeling, but also contains more information than catchment scale lumped modeling. Not only are hill slopes good as a modeling framework, but there have also been a number of important theoretical advancements on runoff processes at the hill slope scale. One example is that convergence and divergence of flow paths along a hill slope can have really big impacts on surface and groundwater hydrographs. So we know that hill slopes matter, the shape of hill slopes matters, and they make up larger landscapes. So it seems important to have a way to quantify the shape of hill slopes. One way of doing this is with the hill slope width function. So to define this, we take an axis down the hill slope from the divide at x equals 0 to the outlet. At each point along the hill slope from x1 to x2 to x3, the width is given by the linear distance between contour endpoints. This results in a width function, which gives the width at each distance from the divide. In this talk, we're going to be thinking about a simplified version of this width function, w, given by an exponential function with the parameters c and a. And a describes the shape of the hill slope, where c describes the width of the divide. So when a is less than 0, we have a convergent hill slope where starting from the divide, it's wider and gets narrower as we move downstream. When a is 0, it's a uniform width hill slope, so it's the same width no matter where you are along the hill slope. When a is positive, it's a divergent hill slope, so the hill slope gets wider as you move downstream. And the morphology or shape of the hill slope has an impact on the shape of the hydrograph. These hydrographs were produced using an analytical model that we developed for overland flow on hill slopes based on hill slope curvature from hill slope width functions. We can see here that the peak flow from the convergent hill slope comes much sooner than that for the uniform or than the divergent hill slope. And in the upper right corner, we see that it also impacts the peak flow rate, where the convergent hill slope has a much higher peak flow rate than the uniform or than the divergent hill slope. But we know that hill slope curvature impacts event hydrographs, so it should also matter for infrastructure design and planning. This is where the rational method comes into this project. The rational method is both the simplest peak flow model and the most widely used. It predicts a design peak flow for a given return period as a function of the runoff coefficient, which is usually chosen from a table in a design manual, a landscape area, which is generally the total catchment area, and then design storm intensity, chosen from an intensity duration frequency curve. Choosing the design storm intensity can be the trickiest part because an intensity duration frequency curve is a whole curve, but we have to choose one value. So the way this is typically done is to choose the storm duration equal to the time of concentration. The time of concentration is the travel time to the outlet from the furthest point in the landscape. So at that point, the whole landscape should be contributing flow to the outlet, which makes it a good assumption to use the whole landscape area for A in the rational method. However, if we go back to the roots of the rational method, we find that the time of concentration is actually an approximation to a different timescale called the critical duration. To understand the critical duration, we have to think about the rational method as the product of 3 curves instead of 3 constants. And the curves would be a runoff coefficient duration curve, not shown here, an area duration curve shown in orange, and an intensity duration curve. And when we multiply these 3 together, we get the white peak flow curve. And the maximum value of this curve is your rational method peak flow. And here we see that that maximum value occurs at the same time that the area duration curve reaches its own maximum. And as I just described, that's the time of concentration. So in this example, the critical duration and time of concentration are the same. So the normal rational method assumptions work, but that's not always the case. Since we have a model for peak flow, which I showed you before, that means from an intensity duration frequency curve, we're able to calculate a runoff coefficient duration curve, an area duration curve, and thus a peak flow duration curve where we can find that critical duration. So just to start, I'm showing you these area duration curves with the intensity duration curves. And it's clear that the shape of the hill slope has a big impact on the shape of the area duration curve, which thus has a big impact on the shape of this peak flow curve. So for the convergent and uniform hill slopes in the top two rows, the critical duration and time of concentration are the same. That's what you want in order to be able to use the rational method. But in the bottom row, the divergent hill slope, the critical duration comes much sooner than the time of concentration. And in this case, if you were to use the peak flow prediction at the time of concentration, then you get a much lower peak flow value than the true rational method prediction at critical duration. So this figure shows theoretical peak flow errors using the rational method as it's traditionally applied. So for convergent and uniform hill slopes, those darker and medium blue values, you see that the critical duration and time of concentration are the same. They're all clustered down at that bottom right corner where the rational method is going to work. But as the hill slope becomes more divergent, the color gets lighter, we move left. So the critical duration becomes more different from the time of concentration. And as that happens, we also move up in the figure, which means that the true rational method peak flow is going to be bigger than what you get using the time of concentration. In this case, there can be a factor of 2 difference. So now we can see that hill slope curvature is really important when considering the rational method. So I'm going to turn it over to Anneliese to show you how we can do these calculations on real hill slopes.
Great. So to summarize, we found that the curvature of a hill slope can greatly impact the peak flow estimates. And coincidentally, we also found that there are very few tools available for practitioners and researchers to either calculate hill slope width functions or to assess the importance of hill slope curvature on peak flow estimates. So as Dana mentioned, we set out to create some of these tools with ArcHydro. We built 4 main ArcHydro tools. 2 of the tools are located in the terrain preprocessing toolbox. The other 2 are located in a new critical duration toolbox. I'll walk through these tools briefly in the next couple slides, and then we'll go through a quick demo. The first tool, Partition Hill Slopes, is located in the terrain preprocessing toolbox and can be used to partition catchments into hill slopes. Before running this tool, the user would need to run standard ArcHydro procedures for catchment delineation, including DEM filling and terrain processing. These procedures give you the right inputs for the Partition Hill Slopes tool. This includes catchments, flow direction raster, flow accumulation raster, drainage lines, and an input flow accumulation threshold that corresponds to the threshold used in catchment delineation. The hill slope delineation tool takes these inputs and first identifies the stream inlet point where the flow accumulation is equal to 0. The tool delineates the headwater catchment draining to this point. Next, it bisects the full catchment with the stream channel, resulting in 2 lateral hill slopes and 1 headwater hill slope. The second tool is the hill slope width function tool and is also located in the terrain preprocessing toolbox. This tool approximates a width function for each hill slope. The inputs to this are just the hill slopes from the previous step, the drainage lines, and a number of points that the user defines. And this number of points is used to be placed along the hill slope outline by the tool. The tool matches these points across the hill slope and computes the width between the matching points as well as their distance to the divide. These values are then plotted, as you can see here on the right, where x-axis is the distance from the divide and the y-axis is the width between these points. These values are used to approximate an exponential function for each hill slope, giving the coefficients c and a, which, as Dana mentioned, tell you about the width at the divide and the shape of the hill slope. We also need to satisfy conservation of area, meaning that we need to make sure that the area of the exponential hill slope matches the actual hill slope area. And we can do this by calculating the length of the exponential hill slope to match the total area of the original hill slope. And finally, we calculate a couple error metrics to help catch cases where the exponential function just doesn't do a very good job of approximating hill slope width. These include an R-squared value that tells you how good the exponential fit is, and also a point error metric, which tells you how well the points chosen approximate the actual hill slope area. So now that we have the hill slopes and an approximation of their shape, we can see how the shape impacts peak flows. We can move into the critical duration toolbox, and the first tool that we have to run is a hill slope roughness tool, which calculates a roughness coefficient alpha. The main inputs to this step are the hill slope width function hill slopes from the previous step, a filled DEM, and a land cover raster from the National Land Cover Database. Alpha is computed as the square root of the slope divided by this Manning's roughness coefficient. And we can get there by using the filled DEM to calculate a slope, and we use the land cover raster from the National Land Cover Database and conversion factors from literature to convert to a Manning's roughness coefficient. And this results in 1 alpha value per hill slope. Finally, the last tool, we can optimize for the critical duration by running the analytical model that Dana described for overland flow on each hill slope for a given return interval storm. The main input for this step is just the alpha hill slopes from the previous step. The user also needs to identify which storm to run. The storm is defined, as Dana mentioned, by an intensity, frequency, duration curve. This curve can be approximated with the power law of the form I equals k over d to the b power, where d is the duration and I is the intensity. So the user just needs to supply the constants k and b. These constants can be found in design manuals or can be approximated by fitting a power law to the IFD curve. So using these inputs, including IFD parameters k and b, as well as a soil saturated hydraulic conductivity, this tool applies the analytical model for overland flow on each hill slope, defined by a width function and a roughness coefficient. The output from this step is a peak flow, Q max, and the time that this occurs, D crit. Also, the time of concentration is calculated, which is the time that the entire hill slope contributes to flow at the outlet. The output ultimately tells the user if the time of concentration is a good approximation to the critical duration. As shown in the figure here, when D crit is less than the time of concentration, using the time of concentration would underestimate peak flows, and D crit should be used instead. Here are just some example outputs from a watershed in California. You can see the partitioned hill slopes on the left in red. We calculate a hill slope width function resulting in convergent, divergent, or uniform hill slopes, or hill slopes that just don't really fit well for an exponential function. We then calculate hill slope alpha, which is used in the critical duration tool, which can tell you how much error there is in your time of concentration value compared to the critical duration value. And so now I'll go into a very brief demonstration of these tools. So starting with hill slope partitioning, the first step. As I mentioned, a prerequisite step is to do terrain processing to generate catchments. One of the outputs from this is a flow accumulation threshold that needs to be pasted into the hill slope partitioning tool. So first we have to copy that value, and then we'll go to our hill slope partitioning tool and paste that into the threshold input. We'll enter the catchments, flow direction, flow accumulation, and the drainage lines, which are all outputs from the terrain processing step. And the automatic output here is just hill slopes. We can press run, and I'm not showing it here because it takes 10 minutes for this large watershed. But then you can see that it's finished. And this is an example of some final partitioned hill slopes. You can see headwater hill slopes in green and lateral hill slopes in purple, with the watersheds in dark in black. And so moving into the second step, hill slope width function, we enter the partitioned hill slopes and the drainage lines. And you can enter any number of points here between 2 and 100. Generally, the more points you add, the longer the tool takes, but it is a better approximation of the actual hill slope shape. And so this takes about 11 minutes, so I'm also not showing that here. We can take a look at some of the results. And one of the main results from this step is the A value. As Dana and I have mentioned, that value tells you about the curvature of the hill slope. So if we just pick two classes, we can classify it into convergent and divergent hill slopes. And we'll set this at 0. So hill slopes with the A value less than 0 are convergent and are shown here in black, and the divergent hill slopes are shown in yellow, where A is greater than 0. Okay, and then moving into the hill slope roughness tool, we enter the hill slope width function hill slopes, and then as I mentioned, we use the National Land Cover Database land cover raster as an input here. So enter that. We also need to put in the filled DEM, and the automatic output is just hill slope width function, critical duration. This step is pretty fast to run. It takes about 1 minute. And we can take a look at the attribute table and see that we've added now the alpha value, the Manning's roughness, and the slope for each hill slope. So this is just an example output of hill slope alpha for each hill slope. So finally, we can move into the fourth step, optimize critical duration. The input is just those alpha hill slopes, and then we have our K and B values for the IFD curve. And we've provided we've provided a range of typical values there and some default values. For the saturated hydraulic conductivity, we'll just assume loam soils in this case. So that takes about 1 minute and 40 seconds for this watershed. And one of the main outputs here, there are a number of outputs, but one of the main outputs is the field DC less than TC, which indicates whether the decrit value is less than the time of concentration. If it is, then curvature could impact peak flow. If it's not less than TC, then curvature probably doesn't impact peak flow, and you could probably use the original rational method or the conventional rational method approach. All right, and with that, I will turn it over to Gina to talk about distributed modeling.
Great, thank you, Anneliese. So yeah, hi everyone. I will be giving just really a teaser into the ArcHydro tools for distributed modeling and kind of bringing these parameter maps that we create with the ArcHydro tools into integrating it with external modeling software. It'll just be a preview, as that will be more heavily discussed in the next webinar. And before diving into that, I do want to take a step back and just outline what the process looks like when we as ArcHydro work with the scientists to collaboratively implement their new tools as ArcHydro tools. So using our collaboration with Dana and Anneliese to bring these new critical duration tools into fruition as an example, there's these two working bodies, the scientists and the ArcHydro team, and this area of overlap where we're working together. So the first step is the scientists and the experts bringing their theory and new application and their starting code to the table. And their first steps to start to transition those into ArcHydro tools are to refactor their code and wrap some of their parameters into those more familiar ArcHydro tool interfaces and bringing those into our kind of standardized script template. And this is once that initial set of code is brought into our template and a tool interface is beginning to be created, that's where that collaboration really starts. So we are really working together as two bodies to do that refactoring of the original code and start to make some parts of executing it more user-friendly so it's accessible to the ArcHydro community. And that's where the ArcHydro team comes in, and we work on helping out with that testing and making tweaks to the code and the tool interface. So that includes things like adding user messages so that users know when they run into an error, what is the cause of it. They can see progress as the tool is running, and also doing things like autofilling the output names in that tool interface to make it easy for users to stick to that ArcHydro naming convention and data model. And from there, really the theory and the code take their final form as ArcHydro tools, as we're seeing there. And once they live in that ArcHydro toolset, that's where the ArcHydro team, for the most part, tries to take over the tasks of, takes over the tasks of maintaining the tools, creating the documentation for them, and the learning materials, again, to increase that accessibility of the new tools to the ArcHydro community and making them as user-friendly as possible. Now moving into that short introduction to the ArcHydro tools that are meant to bridge the gap between the parameter maps and the GIS data that you can create with the tools that we've just previously discussed, and being able to use them to simulate hydrologic processes. So at a high level, this set of tools begins with pre-processing some input elevation data and starting to split those into the hydrologic units, or the catchments, starting to assign where the drainage points are and where those drainage lines are in your system. From there, we start to generate the hydrologic connectivity and really defining that blueprint for how the collective catchments in your system drain into each other. And we're seeing that here shown in that node and link schema. From there, we can calculate the attributes for each catchment that are relevant to hydrologic simulation. So in this way, we can start to model that spatial variability of characteristics that exist in our system and really move along that actual distributed modeling process. So shown here as an example, we start to calculate basin lag, curve number, basin slope, etc. And finally, once we have this pre-processed set of subbasins or hydrologic units that have their relevant characteristics calculated, they have their hydrologic connectivity defined, is where we move into that final export of that set of attributed data to a format that can be ingested by an external modeling software. In our example here, preparing it for HEC-HMS modeling. So just looking quickly at what that geoprocessing tool interface looks like when you have a prepared geodatabase of data, and how we can translate all that information into a basin model file, which will then be ingested by HEC-HMS and be a representation of your GIS and ArcHydro created data as a HEC-HMS model. So in summary, these tools translate that hydrologically attributed data set. Here we're just seeing that smaller data set shown in purple to a HEC-HMS model shown on the right there. And once it's in HEC-HMS, after going through these processes, we can see that basic node link schema representation of our data and the attributes that have been carried over from Pro for each hydrologic component of that model. And from there, I will pass it back to Dan.
Thank you, Gina. If I can catch up with the slides. Well, that was fun. You know, in these webinars, we do not often present the scientific background behind the tools. So this was, for me, an enjoyable departure. And you have also seen a bit of what it takes to take the science and turn it into a production tool. So there is a process that we try to follow when we do that. And finally, let me quickly set the stage for the remaining presentations in the series. And on April 15th, we'll focus on integration with external H&H models, and we'll talk about model integration in general. So you've seen a little bit of that today with HEC-HMS. We'll extend that to HC-RAS, and we'll talk about ICPR, and we'll talk about node flow, and we'll talk about generic way of trying to integrate with your own models so you can take the GIS infrastructure and basically support any type of H&H modeling activity that you need. And then we'll wrap up the whole webinar series. We'll talk a little bit more about the data, some of your questions that came over the whole series, and we'll have some fun. And with that, let's take some questions. And before we do that, I will go back to the ArcHydro links page as a reference. And Krista, back to you. Let's do some questions.
Thanks, Dan. We do have quite a few questions coming in, and we still have quite a bit of time, so I think we might be able to get to most of them. Let's start with Heather. She submitted a question. She wants to know, do you use Ks for the texture of the first soil horizon? How do you account for different soil textures near the soil surface as you head downstream? And this came in during Dana and Anneliese's presentation, so one of you guys are probably up for the answer.
I can, I'll take it.
Okay.
So the KS value in the tool is really just an average KS value, and I think it would be taken from the top of the soil horizon because this is simulating overland flow processes. In future development of this tool, it's possible that we could take, for example, soil shapefiles from NRCS that have that KSAT value integrated, and so it's possible that we could integrate that into future tool workings, but for now it's really just an average KS value.
Thanks, Anneliese. We had several attendees ask questions about the rational method and if there's a limitation for size. So they're asking, like, if there's a limitation, what is the size, or is there a way to control for that, as in this area that they're...
Yeah, I can take that one. The rational method is generally only used on small landscapes. That's why it's appropriate for comparison to this Hillslope scale model that we're using. It's common to limit the size at 2 acres, 200 kilometers squared, something like that. And this tool, I think, Anneliese, is there a functionality in there to limit the size of the hill slopes? I know we talked about that. Did we implement that?
Yeah, so that would come in the catchment delineation phase, where you would set the flow accumulation threshold to kind of limit the size of your catchments that you're delineating.
Thanks, ladies. This might be one for Dan. We had a couple questions about the functionality of what was shown today in ArcMap versus ArcGIS Pro.
So the new functionality with Hillslope analysis and the rational method, that is available only in Pro and not in ArcMap. The StreamStats part that can be used in both, this involves all the terrain preprocessing and watershed delineation and characterization that's covered in both platforms.
Thanks, Dan. We have another question about soil coming in from Druv. Can we use soil type layer instead of the national land cover data?
I assume that is in reference to the roughness tool. The quick answer is no. You have to use the land cover database raster for that tool. But there are some workarounds. Like if you want to calculate your own roughness value, you could do that on your own and just make sure that the fields and that final output match what you would get using the National Land Cover database. So that is a slope, an N value, and an alpha value. So as long as you have those fields, you can run the next tool.
Thanks, Anneliese. We're getting a lot of questions from attendees about the PowerPoint and the recording. The recording of this webinar will be posted on the registration page. You'll see if you go there right now that the first two webinars are on demand and you can watch it at your convenience. This webinar will also be posted sometime next week. And the PowerPoint presentation will be posted in our water resources community, which I see Mariah added a link to our chat box. So if you check the chat box, you'll see a link to our community and the PowerPoint will be loaded there. So you'll have access to the slides and the recording next week sometime. Let's keep moving. We still do have a few minutes. We're getting several questions about rainfall runoff modeling using ArcHydro. Would the team, any of you, want to discuss that a little bit?
Well, let me take that. If you want to do the traditional rainfall runoff modeling in a deterministic way, we are going to talk a little bit more about that on the next one, where we are talking about the integrated GIS and H&H modeling. The typical process would be to, let's say, develop your deterministic model like HMS or ICPR or SWIM if you want some components of it, and then take the precipitation or snow as an input into that model. Your input layers would be precipitation or snow, and all the elements that go into the development of your basin files for your deterministic hydrologic model. So the numerical processing itself would be done in an external application like HMS or ICPR. We have, in a way, in a rational method, also there is the discussion about the intensity, which is your precipitation reference in your hydrologic model. So there are different ways of handling that. But in a broader context, we'll talk more about that next time.
Thanks, Dan. We have a less specific question coming in from Bill Saunders. He wants to know if the Hillslope scale model of subbasins is an Esri specific implementation, or do you know if it has, or something like it, been applied at the National Water Center? I know you work with them, Dan.
Yeah. No, I do. So, hi, Bill. So let's do this two ways. So let's first, Dana, why don't you comment in general on the Hillslope approach, and then I'll talk about specifically what's happening at the National Water Center.
This Hillslope approach, where we use the Hillslope width function to simulate morphology for the overland flow, there are a couple other similar analytical models that exist for this in the literature. The one that we developed is available freely, implemented in a Jupyter notebook on my GitHub site, which we can provide the link for later if someone's interested.
Yeah, and one of the things that, and so this kind of goes back to Gina's slide on interaction. What we like with the way we are implementing tools, especially now on Pro End, it's all really Python code, right? So, and it's open, so you can take it, you can look at it, you can edit. don't call it ArcHydro Tools anymore if you make edits, right? If you want to contribute, let us know, because we're on the hook to maintain it. So, that's the beauty. So it makes it much more accessible. In relationship to the implementation at the National Water Center, at this point, no, that's not implemented. Once we get this fully in ArcHydro and we get some feedback from our users, we'll see what the opportunities are for broader implementation. And it's really, let me turn the tables a little here. We, as the ArcHydro team, are in business of developing some interesting tools as driven by our user community, you. And we had this wonderful opportunity to work with Dana and Anneliese to bring these tools, the science tools, into our ArcHydro community. Now, we would like you, as the community, to use these tools and have fun with them and tell us what works well and apply the science in your environment and let us know how it goes. And then in our community page, write a little blog, say this works, this doesn't work, and get back in touch with us to improve the tools or the process. So that's my plea to you to get involved.
That's a great point, Dan. We do look at those community comments in our pages, so please do get involved. I mentioned before that Mariah's included a link in our chat window. If you're not already a member, go ahead and check out our water resources community, become a member, and this is the best place to post your feedback, comments, and even questions. If you're using the tools and you come across some struggles or challenges, join the group, chat it up in there. Someone's always going to respond to you. The community is really great at helping each other, but Esri staff is also involved in that community, and you'll get responses from our Esri professionals as well. We have a couple minutes left. I don't know if you want to get into this, Dan, but we do have several attendees asking if there's any kind of tools in development or resources for integrating the surface water work with groundwater.
Okay, so let's see, what do we have? A couple of minutes.
Yeah, you're gonna have to make it short.
That's a problem. What we'll do is we'll talk about groundwater integration a little bit more in the next webinar. We'll talk about the ArcHydro groundwater a little bit and our interaction with Aquaveo and their tools in the groundwater domain. So let's leave it for then. And I'll basically pick up that question and try to answer in the next webinar to a little bit bigger extent.
It's a good pitch, Dan. So everyone needs to register for the next webinar, and you'll find out more about that integration with groundwater. I have one question I'm going to throw at you. It should be a pretty easy one. Thomas is asking, where does he find these hand tools? He can't find them in his ArcHydro toolbox. Is there somewhere else he should be looking?
So the hand tools, there are two sets of tools. The basic hand tools are in the H&H modeling tool set, in the ArcHydro tool set. If you cannot find it, shoot me an email. Make sure you are using the latest version of the tools for your desktop platform. They should be there. We have more broad set of tools that will be dealing with specific data sets, like leveraging NHD plus high res within hand and national water model context. These tools are being tested and have not been released in the what I call ArcHydro proper. So they should be coming in next couple of weeks, and I'm giving myself a deadline definitely before our webinar in April.
Perfect. Thanks, Dan. And thank you to our special guests, Dana, Anneliese, and Gina. Thank you, everyone, for attending. And we hope to see you on the last webinar of our ArcHydro webinar series. Have a great evening, day, morning, wherever you are in the world. We hope to see you next time.
Thank you.
Thanks, everyone.
Bye.